Quantum Weirdness, Chapter 4 and the Conclusion, the Einstein-Bohr Crapshoot. Whereas Einstein didn't believe in a god that plays dice in the universe, Bohr not only accepted such indeterminacy, but also pointed out that it was part and parcel of how we understand the world of physics. Interestingly, Bohr not only acknowledged the cosmic crapshoot, but pointed out that such a game was played in the dark, and it was only when we shined some light on the proceedings that we could determine its present outcome. Ironically, our very act of illuminating the hidden play fundamentally alters what we unearth. It is as if God is playing poker in the dark, and we cannot see what hand he is holding until we turn on the lights. But that very act of turning on that light can in and of itself change a face card to a number card or vice versa. Nature is like a very fine and delicate Swiss watch with many extraordinarily small and complicated and interlocking pieces hidden behind a silver chamber. We are like a brutish man with very large hands whose fingers lack any finesse or dexterity trying to figure out exactly how that watch works. But every time we try to understand its sophisticated mechanism, we invariably mangle its parts by our clumsiness. Thus, our very act of trying to understand or fix the watch changes, to some degree, its constituent parts. It is for this reason that Bohr could say with confidence that we don't see nature as nature, but as nature is revealed to us through our acts of measurement, which may be more accurately described as acts of intrusion. Both Bohr and Einstein were troubled by the new physics, and the decades-long debate they carried on over the implications of quantum theory provides us with one of the great philosophical debates of the 20th century. Some commentators have outlined the Einstein-Bohr debate into 4 stages, starting with the Solvay Conference of 1927. Others have suggested that the debate took 2 major developments, while still others have argued that it was rather just one long debate that evolved over time. Regardless of how the Einstein-Bohr debate is partitioned, it is widely accepted that the discussion got its first fireworks at the 5th Conference of Physics at Solvay when Einstein strenuously objected to quantum indeterminacy. Einstein ingenuously came up with thought experiments that tried to show how uncertainty relations could be overcome, and thus violate the notion of indeterminacy. At first, Einstein's critique was predicated upon a modification of the famous double-slit light experiment, where he suggested that some form of measurement, albeit merely theoretical and infinitesimally small, could indeed be made which would violate the notion of indeterminism. At first, it looked as if Einstein had provided a penetrating body blow to the new physics, but Niels Bohr brilliantly demonstrated that even in light of Einstein's updated modification, it would still be impossible to gather the precision necessary to refute indeterminacy. As one commentator summarized its more technical aspects, Bohr observes that extremely precise knowledge of any potential vertical motion of the screen is an essential presupposition in Einstein's argument. In fact, if its velocity in the direction x before the passage of the particle is not known, with a precision substantially greater than that induced by the recoil, that is, if it were already moving vertically with an unknown and greater velocity than that which it derives as a consequence of the contact with the particle, then the determination of its motion after the passage of the particle would not give the information we seek. However, Bohr continues, an extremely precise determination of the velocity of the screen, when one applies the principle of indeterminacy, implies an inevitable imprecision of its position in the direction x. Before the process even begins, the screen would therefore occupy an indeterminate position at least to a certain extent, defined by the formalism. The problem that was haunting Einstein here was one of measurement, since if he could show, even theoretically, that it was possible to get a precise fix on a quanta event, it would violate Heisenberg's principle of uncertainty and show prima facie that realism could be reintroduced into the new physics. In their first formal confrontation over this matter, even despite Einstein's cleverness, Bohr showed conclusively how Einstein's thought experiment was in error. At the next Solvay conference, however, held in 1930, Bohr had a much more difficult time overcoming what became infamously known as Einstein's box. This thought idea is actually fairly straightforward and not difficult, even for us armchair observers, to comprehend. Again, relating to Heisenberg's principle of uncertainty, Einstein imagined a box which contained a certain limited amount of electromagnetic radiation and which was trapped within a certain small region. Adjacent within the box was a clock which was connected to a small aperture which, given a set time, would release a photon, or small packet of radiation, from within the trapped box, thereby decreasing the amount of energy it originally contained. Connected outside of this box was a weighing scale which allowed for measuring the weight within the box before and after the photon or radiation was released. This would conceivably allow for two differing weights and thus provide one with a certainty hitherto not allowed under uncertainty relations. This thought experiment is based in part upon Einstein's famous equation of E equals sign mc2, where matter is literally congealed energy and thus carries weight which is amenable to some form of measurement. Imagine the weight of Einstein's box with some bundled radiation, and imagine the weight of that same box which has released through its portal a quanta of energy. It should be possible, given this scenario, which also contains a clock to accurately provide the time when that photon is released, to gather precise information about such electromagnetic energy that is not allowed under indeterminate coordinates. In sum, Einstein's box should contradict indeterminism and thus allow for a realistic interpretation, and not merely a probabilistic one, for what transpires at the subatomic realm. The simplicity of the experiment makes it look at first glance exceedingly convincing. Indeed, it did look to be true, even to Bohr, who apparently was flummoxed when he first learned of it. As Leon Rosenfeld commented, it was a real shock for Bohr, who, at first, could not think of a solution. For the entire evening he was extremely agitated, and he continued passing from one scientist to another, seeking to persuade them that it could not be the case, that it would have been the end of physics if Einstein were right, but he couldn't come up with any way to resolve the paradox. I will never forget the image of the two antagonists as they left the club. Einstein with his tall and commanding figure, who walked tranquilly with a mildly ironic smile, and Bohr who trotted along beside him full of excitement. However, Bohr eventually saw the flaw in Einstein's box, and through a crafty use of reasoning, which ironically employed using Einstein's own great discoveries against himself, he was able to show why the device wouldn't work as predicted. As one commentator elaborates, the triumph of Bohr consisted in his demonstrating once again that Einstein's subtle argument was not conclusive, but even more so in the way that he arrived at this conclusion by appealing precisely to one of the great ideas of Einstein, the principle of equivalence between gravitational mass and inertial mass. Bohr showed that, in order for Einstein's experiment to function, the box would have to be suspended on a spring in the middle of a gravitational field. In order to obtain a measurement of weight, a pointer would have to be attached to the box which corresponded with the index on a scale. After the release of a photon, weights could be added to the box to restore it to its original position, and this would allow us to determine the weight. But in order to return the box to its original position, the box itself would have to be measured. The inevitable uncertainty of the position of the box translates into an uncertainty in the position of the pointer, and of the determination of weight, and therefore of energy. On the other hand, since the system is immersed in a gravitational field which varies with the position, according to the principle of equivalence, the uncertainty in the position of the clock implies an uncertainty with respect to its measurement of time, and therefore of the value of the interval at ba. A precise evaluation of this effect leads to the conclusion that the relation cannot be violated. After the 6th physics conference at Solvay, Einstein took a different line of criticism, since he apparently accepted, at least temporarily, the recalcitrant inherency of uncertainty. Rather, Einstein argued that though quantum mechanics provided much headway into the more esoteric realms of physics, it was nevertheless an incomplete theory. As Einstein explained, I have the greatest consideration for the goals which are pursued by the physicists of the latest generation, which go under the name of quantum mechanics. And I believe that this theory represents a profound level of truth, but I also believe that the restriction to laws of a statistical nature will turn out to be transitory. Without doubt, quantum mechanics has grasped an important fragment of the truth and will be a paragon for all future fundamental theories, for the fact that it must be deducible as a limiting case from such foundations, just as electrostatics is deducible from Maxwell's. Equations of the electromagnetic field, or as thermodynamics, is deducible from statistical mechanics. Perhaps the height of the Einstein-Bohr debate happened in 1935 when Einstein, along with Boris Podolsky and Nathan Rosen, published a landmark paper in Physical Review under the title, Can quantum mechanical descriptions of physical reality be considered complete? This paper, perhaps more than any other Einstein has written, has generated the most heated debate about quantum theory. Because at the time it was written, its profound implications were mostly overlooked or prematurely dismissed. An abstract of the paper, which was published in Volume 47, Issue 10, see pages 777 to 780, of Physical Review is deceptively simple. In a complete theory, there is an element corresponding to each element of reality. A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty, without disturbing the system. In quantum mechanics, in the case of two physical quantities described by non-commuting operators, the knowledge of one precludes the knowledge of the other. Then either 1, the description of reality given by the wave function in quantum mechanics is not complete, or 2, these two quantities cannot have simultaneous reality. Consideration of the problem of making predictions concerning a system on the basis of measurements made on another system that had previously interacted with it leads to the result that if 1 is false, then 2 is also false. One is thus led to conclude that the description of reality as given by a wave function is not complete. It turns out to be one of the great ironies of this famous paper is that it ended up providing a very strong case for, and not against, quantum mechanics. What the paper sets out to do, more formally, is this, according to Wikipedia's entry on EPR. The EPR experiment yields a dichotomy. Either 1. The result of a measurement performed on one part A of a quantum system has a non-local effect on the physical reality of another distant part B, in the sense that quantum mechanics can predict outcomes of some measurements carried out at B, or 2. Quantum mechanics is incomplete in the sense that some element of physical reality corresponding to B cannot be accounted for by quantum mechanics. That is, some extra variable is needed to account for it. At the time that this paper was published, it was not yet known how to test its basic hypothesis, and thus it was attacked on more theoretical grounds, or as in the case of Wolfgang Pauli, discounted without due consideration. Just months after Einstein's collaborative paper was published in 1935, Bohr published his own rejoinder, with the same title as Einstein's, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? In the same Physical Review in Volume 48. Issue 8, pages 696, 702. Although Bohr didn't provide an experiential rebuff to Einstein, he did lay out his point-by-point critique. Argued Bohr, such an argumentation, however, would hardly seem suited to affect the soundness of quantum mechanical description, which is based on a coherent mathematical formalism covering automatically any procedure of measurement like that indicated. The apparent contradiction, in fact, discloses only an essential inadequacy of the customary viewpoint of natural philosophy for a rational account of physical phenomena of the type with which we are concerned in quantum mechanics. Indeed, the finite interaction between object and measuring agencies, conditioned by the very existence of the quantum of action, entails, because of the impossibility of controlling the reaction of the object on the measuring instruments if these are to serve any purpose, the necessity of a final renunciation of the classical ideal of causality, and a radical revision of our attitude towards the problem of physical reality. In fact, as we shall see, a criterion of reality like that proposed by the named authors contains, however cautious its formulation may appear, an essential ambiguity when it is applied to the actual problems with which we are here concerned. To understand at what is stake, it is perhaps important here to introduce the concept of quantum entanglement, where two electrons, each with opposite spins, are forever engaged with each other such that a decisive change of one electron's spin from upward to downward must, because of quanta superposition of two states, change the other twin's electron spin from downward to upward, and vice versa. A more technical yet precise explanation is provided by David Bohm, J. Hiltz, and others. The following excerpt from an entry on quantum entanglement from the online encyclopedia Wikipedia appears based, at least in part, upon J. Hilt's 2007 paper in the Journal of Physics. We have a source that emits pairs of electrons, with one electron sent to destination A, where there is an observer named Alice, and another is sent to destination B, where there is an observer named Bob. According to quantum mechanics, we can arrange our source so that each emitted electron pair occupies a quantum state called a spin singlet. This can be viewed as a quantum superposition of two states, which we call state 1 and state 2. In state 1, electron A has spin pointing upward along the z-axis plus z, and electron B has spin pointing downward along the z-axis in z. In state 2, electron A has spin z's, and electron B has spin plus z. Therefore, it is impossible to associate either electron in the spin singlet with a state of definite spin. The electrons are thus said to be entangled. Alice now measures the spin along the z-axis. She can obtain one of two possible outcomes, plus z or z. Suppose she gets plus z. According to quantum mechanics, the quantum state of the system collapses into state 1. Different interpretations of quantum mechanics have different ways of saying this, but the basic result is the same. The quantum state determines the probable outcomes of any measurement performed on the system. In this case, if Bob subsequently measures spin along the z-axis, he will obtain z with 100% probability. Similarly, if Alice gets z, Bob will get plus z. There is, of course, nothing special about our choice of the z-axis. For instance, suppose that Alice and Bob now decide to measure spin along the x-axis according to quantum mechanics. The spin singlet state may equally well be expressed as a superposition of spin states pointing in the x direction. We'll call these states Aya and Ie. In state Aya, Alice's electron has spin plus x and Bob's electron has spin plus x. In state Taye, Alice's electron has spin plus x and Bob's electron has spin plus x. Therefore, if Alice measures plus x, the system collapses into Ia, and Bob will get x. If Alice measures x, the system collapses into ECA, and Bob will get plus x. In quantum mechanics, the x-spin and z-spin are incompatible observables, which means that there is a Heisenberg uncertainty principle operating between them. A quantum state cannot possess a definite value for both variables. Suppose Alice measures the z-spin and obtains plus z, so that the quantum state collapses into state 1. Now, instead of measuring the z-spin as well, Bob measures the x-spin. According to quantum mechanics, when the system is in state 1, Bob's x-spin measurement will have a 50% probability of producing plus x and a 50% probability of sa. Furthermore, it is fundamentally impossible to predict which outcome will appear until Bob actually performs the measurement. So, how does Bob's electron know, at the same time, which way to point if Alice decides, based on information unavailable to Bob, to measure x, and also how to point if Alice measures z? Using the usual Copenhagen interpretation rules that say the wave function collapses at the time of measurement, there must be action at a distance, or the electron must know more than it is supposed to. To make the mixed part quantum and part classical descriptions of this experiment locale, we have to say that the notebooks and experimenters are entangled and have linear combinations of plus and written in them, like Schrödinger's cat. As this is a fairly complicated and technical feature in quantum mechanics, varying physicists from Erwin Schrödinger, thus the famous Schrödinger's cat, to David Bohm, have tried to explicate it by using ordinary objects that we are all familiar with. To further illustrate what is at stake here, and to perhaps underline why quantum mechanics has been described as weird, imagine that the paired electrons are actually a deeply in love married couple far into the future. After their initial honeymoon, the couple, we will call them Brad and Angelina, has to go back to work on their respective planets. They met on an interstellar dating service over the Trans-Galaxy Web Service, which are in completely different solar systems separated by 1 billion miles. Since our entangled pair, like their electron counterparts, represent the dynamic fusion of opposing spins, the female-male interplay. Further imagine that if Brad was to have a sex change operation and turn himself into a she, his wife, Angelina, must, given this obviously forced analogy, in turn change herself into a he. The question that arises here, as it does with paired electrons, is how long would the change take and how would it be implemented? In other words, how would Angelina find out that her lover Brad has become her so that she may become him? In a conventional physics sense, we are tackling the issue of how information travels and how long it takes to traverse spatial distances. More pointedly, We are coming to grips with the very foundation of modern physics and how matter behaves. At the quantum level, however, we have discovered that things operate quite differently than we ever expected. Given the speed limit that has defined how fast objects can travel, basically the speed of light, 186,000 plus miles per second, we would expect the information about Brad's sex change to reach Angelina in about an hour and a half, give or take a few minutes depending on initial conditions. What we would not expect is for such information to reach Angelina in no time at all. It was in reaction to this absurd claim, something non-local could actually influence a very specific local event, that Einstein used his pithy phrase, "spooky actions at a distance." In his 1935 paper with Podolsky and Rosen, Einstein had no idea at the time that the very objection he was making about quantum theory was in itself the basis for a hypothetical experiment which would decades later actually be performed and show quite conclusively that spooky action at a distance, or non-local interference, was indeed part and parcel of quantum reality. Writes Einstein. One could object to this conclusion, the one Einstein was making about quantum theory not being complete, on the grounds that our criterion of reality is not sufficiently restrictive. Indeed, one would not arrive at our conclusion if one insisted that two or more physical quantities can be regarded as simultaneous elements of reality only when they can simultaneously measured or predicted. On this point of view, since either one or the other, but not both simultaneously, of the quantities P and Q can be predicted, they are not simultaneously real. This makes the reality of P and Q depend upon the process of measurement carried out on the first system, which does not disturb the second system in any way. No reasonable definition of reality could be expected to permit this. But this very last quoted line in what is known more commonly as the EPR paper, so named because of the initials of the three authors, is precisely what does happen in quantum entanglement. It is precisely what does happen when Brad gets a sex change operation on a distant planet and becomes a female, and Angelina instantly turns into a man, even though she is a billion miles away. Einstein's spooky actions at a distance are right, even if he coined that phrase as a pejorative slight on the utter silliness of the notion. At the time of this paper, however, there was no way of knowing that it would serve as the impetus for J.S. Bell to devise an experiment to find out if hidden but local events were really transpiring at the quantum level, or rather if quantum mechanics was indeed a complete description and something non-local was occurring. As J. Hiltz wrote in his review of Einstein and Bohr's 1935 papers, with these results, as shown in Bohr's experiment as mentioned in his paper, Bohr claimed that the description of physical reality given by EPR was wrong. Their conclusion regarding the quantum mechanical incompleteness of the description of reality is thus also false. The conclusions of the EPR paper try to resolve this paradox by stating that quantum mechanics is merely a statistical approximation of a more complete description of nature, which has yet to be discovered. In this more complete description of nature, there exists variables pertaining to every element of physical reality. There must be, however, some unknown mechanism acting on these variables to give rise to the observed effects of non-commuting quantum observables. Such a theory is called hidden variable theory. John S. Bell derived a set of inequalities, known as Bell's inequalities, which showed that the predications, predictions, CO, of quantum mechanics through the EPR thought experiment actually differed from the predictions of various hidden variable theories. These predictions have much stronger statistical correlations between measurement results performed on different axes than the hidden variable theories. These theories are generally non-local. Recall the EPR paper used locality as one of their arguments. Today, most physicists believe that the EPR paradox is only a paradox because our classical intuitions do not correspond to physical reality in the realm of quantum mechanics. Although Bohr wrote a fairly lengthy critique of Einstein's position, he didn't know enough at the time of non-local variables to drive home the point that spooky action at a distance is indeed allowed and predicted by quantum theory. Indeed, if non-local influences would have been known then, Einstein couldn't have written, "No reasonable definition of reality could be expected to permit this." Yet 5 decades later, such a definition of reality, albeit at the quantum level, turned out to be both reasonable and true. In 1974, Aspect began probing the subject, building upon the pioneering work of John Clauser and collaborators. He understood how to test the locality hypothesis, central in the controversy. He developed polarizers whose settings could be changed every 10 nanoseconds and set up a source of entangled photons with an unprecedented efficiency. The key experiments, carried out at Orsay in 1982 by Aspect, Philippe Grangier, Gerard Roger, and Jean Dalibard, showed a clear violation of Bell's inequalities in conditions closely resembling the ideal Gedanken experiment. The foundation for the theoretical discussions, quantum theory was once again vindicated. A pair of entangled photons should be considered as a global, inseparable quantum system, Aspect concludes. 20 years later, it appears this work has helped in launching the second quantum revolution, with promises for quantum cryptography and quantum information processing. Conclusion: who won the game? The most interesting feature of the Einstein-Bohr debate is that even though both physicists have been dead for over nearly a half-century, Einstein in 1955 and Niels Bohr in 1962, the debate they started in the 1920s is still continuing. Some physicists, such as David Bohm, have championed newer versions of realism where quantum indeterminacy is resolved by introducing such notions as the pilot wave model, which allows for reintroducing actual positions for particles without the traditional invocation of a special and somewhat obscure status for observation. As the Stanford University Encyclopedia on Philosophy explains, Bohmian mechanics, which is also called the de Broglie-Bohm theory, the pilot wave model, and the causal interpretation of quantum mechanics, is a version of quantum theory discovered by Louis de Broglie in 1927 and rediscovered by David Bohm in 1952. It is the simplest example of what is often called a hidden variables interpretation of quantum mechanics. In Bohmian mechanics, a system of particles is described in part by its wave function, evolving as usual according to Schrödinger's equation. However, the wave function provides only a partial description of the system. This description is completed by the specification of the actual positions of the particles. The latter evolve according to the guiding equation, which expresses the velocities of the particles in terms of the wave function. Thus, in Bohmian mechanics, the configuration of a system of particles evolves via a deterministic motion choreographed by the wave function. In particular, when a particle is sent into a two-slit apparatus, the slit through which it passes and where it arrives on the photographic plate are completely determined by its initial position and wave function. Bohmian mechanics inherits and makes explicit the non-locality implicit in the notion, common to just about all formulations and interpretations of quantum theory, of a wave function on the configuration space of a many-particle system. It accounts for all of the phenomena governed by non-relativistic quantum mechanics, from spectral lines and scattering theory to superconductivity, the quantum Hall effect, and quantum computing. In particular, the usual measurement postulates of quantum theory, including collapse of the wave function and probabilities given by the absolute square of probability amplitudes, emerge from an analysis of the two equations of motion, Schrödinger's equation and the guiding equation, without the traditional invocation of a special and somewhat obscure status for observation. While still other physicists, such as Hugh Everett, have extended the logical implications of quantum indeterminism and postulated a many-worlds hypothesis, whereby there are myriads of worlds in the universe in addition to the world we are aware of. In particular, every time a quantum experiment with different outcomes with non-zero probability is performed, all outcomes are obtained, each in a different world, even if we are aware only of the world with the outcome we have seen. In fact, quantum experiments take place everywhere and very often, not just in physics laboratories. Even the irregular blinking of an old fluorescent bulb is a quantum experiment. A growing number of physicists today are taking a fresh look at the philosophical implications of the Einstein-Bohr debate and suggesting that Einstein's objections to quantum theory being incomplete deserves more attention. Others have suggested that the debate can only be resolved by trying to find a grand unified theory that unites gravity with electromagnetism. Philosophically, the issue of realism in physics versus statistical approximations is a profound one and has implications for fields ranging from evolutionary psychology to Bayesian probability theories in neuroscience. As for an ultimate winner of the Einstein-Bohr debate, it may well be that the answer to that question is as indeterminate as the position of a single photon.